This last experiment of the course is called the rolling can. We've already considered situations of objects sliding down an inclined plane and determining the constant acceleration. What you've been discovering in this lesson is that it's not quite that simple. In addition to the translation of an object as it goes down the plane, it can also be rotating. And if it's rotating, there's a torque. If there's a torque, there's an angular acceleration. And because it's spinning in a circle, there's going to be an energy associated with that, a rotational kinetic energy. In this lab, you are going to take a can and allow it to roll down the ramp and across a tabletop. We'll measure some values for it on the ramp and across the tabletop, and use those numbers to demonstrate the rotational mechanics relationships. We'll consider the rotational dynamics, we'll consider conservation of energy, and then finally, we'll talk about angular momentum. You'll be able to see these relationships and the equations and how these different quantities are related to each other.
The materials for this experiment are a grocery can, a ramp, meter stick, timer, and ruler. Here is an example of the motion of a can rolling down a ramp and across a flat surface. The quantities to be measured include the mass and diameter of the can, the distance traveled down the ramp, d, the time of travel on the ramp, delta t1, the vertical height at the release point, y, the distance traveled on the flat surface, delta x, and the time corresponding to that distance, delta t2. Data analysis will include examination of translational and rotational kinematics, rotational dynamics, conservation of energy, and angular momentum. First, determine the acceleration on the ramp and the speed of the can on the flat surface, along with the corresponding rotational quantities. The acceleration on the ramp is twice the distance down the ramp divided by the square of the time. The corresponding angular acceleration is that translational acceleration divided by the radius of the can. The speed on the horizontal surface is the change in position over the change in time. The corresponding angular velocity is that translational velocity divided by the radius of the can. For rotational dynamics, use the moment of inertia and applied torque to find the angular acceleration and compare it to the kinematic values. Note that the applied force, the static frictional force, is the x component of the gravitational force, which is mass times gravity times the sine of the angle, which in this case happens to be the vertical height y divided by the distance down the ramp, d, the hypotenuse of the right triangle. The torque is that force multiplied by the radius of the can, since the two vectors must be perpendicular to each other. The angular acceleration is the torque divided by the moment of inertia. Next, analyze the motion in terms of energy conservation. Compare the initial potential energy of the can at rest at the top of the ramp to the sum of the translational and rotational kinetic energies at the bottom of the ramp. The relationship between the translational velocity and the rotational velocity, v and omega, has already been given under the translational and rotational kinematics page. Finally, compare the change in angular momentum as the product of the torque and the time down the ramp to the final angular momentum of the can, since the can starts from rest. Therefore, the change in angular momentum is simply the moment of inertia times the final angular velocity minus 0.